The first talk of the session is by James Parker from Galois, and the title is FROMAGER, a scalable toolchain for complex zero-knowledge proofs about software. Please.
Okay, thanks, Ron. I'm James Parker. I work at Galois, and today I'll be telling you a little bit about some of the research we've been doing on the DARPA Civ program, and our project is called FROMAGER. So in our project, we're doing research on proving properties about programs in zero knowledge. So by properties, we're focusing on two main things. So either proving that vulnerabilities exist in your program while keeping the triggering exploit secret, and on the other side, we're proving the safety of your code while keeping the source code secret. Today, I'll be focusing on the first one of these tasks, and we want to do so efficiently, right? So we want to do so quickly and while minimizing communication costs between provers and verifiers. So one question to ask is, should you disclose software vulnerabilities? So I think most of us would agree, yes, you should, right? If you're a white hat hacker, maybe you find a 0-day and you go to a company and you present your exploit, and then maybe if you're lucky, they give you a bug bounty and you're really happy and they fix it and users are safer because of this. Well, that's great if that happens, but oftentimes in practice, this doesn't happen. Maybe vendors ignore you, or they say, oh, that's not an issue, or whatever. So what do you do about this? Well, one thing you could do is you could publicly disclose the vulnerability, but that isn't so great, because then bad actors can take the code or take the exploit, and then it puts users at risk and threatens their security. So our solution to this problem is to generate zero-knowledge proofs that demonstrate that you hold or know an exploit to a program, but you use the zero-knowledge proof to keep the actual exploit secret. So here's a very high-level picture of our system. It's called FROMAGER. So here on the left, you can see we take as input a public input program. So we can support any LLVM program. So that means programs like C, C++, Rust. And then also in our system, we take as input the exploit that triggers the vulnerability. And then at the end of the day, we generate a zero-knowledge proof that this vulnerability occurred. So here's some of the capabilities that we've demonstrated so far. So we've demonstrated buffer overflows in the GRIT program, which is a Game Boy Advanced Imaging Transmogrifier program. In FFmpeg, so this is a video codec library that's used in Firefox, Chrome, VLC, and YouTube. And we've also proved information leakage vulnerabilities. So we've proved the Heartbleed vulnerability in OpenSSL. And we're also working on proving cryptographic protocol bugs. So for instance, in the scuttlebutt implementation. And just to highlight, so these are the sizes of the circuits that we're generating. So we're generating circuits on this from 27 million AND gates to all the way up to 17 billion AND gates. So here, our system is split into two components. We have a front end that is a compiler that generates a circuit from the input program. And then on our back end, we have an interactive zero-knowledge proof back end that takes the circuit program and the secret trace input and then runs the zero-knowledge protocol between the prover and verifier. So first, I'll talk about our front end. So like I mentioned, we have this compiler from LLVM. We generate an assembly program. We call our internal IR assembly language microRAM. So microRAM is derived from tinyRAM, if you're familiar with that work, from the Snarks for C paper. We also take as input the exploit. We generate a circuit for this microRAM program. And we also generate all the advice that's the secret trace of the execution of the program. So what goes into this circuit? So this is all a review of prior work in TinyRAM. So like I said, the trace is a witness that's made up of all the states of the execution of the program. In the states, it's made up of all the registers, the program counter, and we also have a flag that indicates whether or not a vulnerability has been proven so far in the execution of the program. And the circuit is made up of two main components. One is the state transition function, which takes a step from one state to the next state in the circuit. And then we also have a memory consistency check that ensures that all memory operations were valid with respect to the execution of the program. So here's a high-level a pseudocode of represents the state transition function. Here you can say we take the current state as input. We fetch the current instruction based on the program counter of the current state. We look up the arguments for that instruction. And then given the opcode, we mux over all the potential opcodes in our microRAM language and then generate the circuit based off of that. So this is a high-level overview of our state transition function. So we also do a memory consistency check. This is also what TinyRAM does. Basically, you sort all the memory operations that happen in the program by address and then the cycle count of when that operation happened. And you basically need to ensure that all the reads that happen match the previous writes to that address. And you can do this in a linear pass over all the memory operations. And then you also need to check that all these sorted memory operations match what actually happened in the program's execution. And you can do this with a permutation check. So here's the whole circuit at a high level. You can see we have the states that are our advice, and then we have memory operations. And then we combine these two types of circuits together to build our overall circuit. OK, so what have we done in our work? So we've made some optimizations to minimize the sizes of the circuits that we generate. So we call these sparsity and public PC. And then we have efficient encodings to detect vulnerabilities in zero knowledge. And so far, we can detect memory errors and information leakages. So for the sparsity optimization, we had this realization that certain instructions are expensive and aren't used very frequently. So an example of this is our memory operations. So what if we don't actually run the checks for these instructions at every cycle? So this actually gives us savings because we don't need to generate all the memory checking circuitry that's used at every single instruction step. And this results in a savings in circuit size since those memory operations are only inserted every n instructions. So here you can see now instead of each state transition function having its own memory check, they share every two state transition functions share a memory operation check. So the next optimization we've implemented is an optimization we call public PC. So encoding this state transition function it's expensive. It has a lot of overhead since you need to mux over all the instructions. So in this case, what we do is we generate circuits for frequently used or likely to be used basic blocks in the program. So this gives us savings because the program counter in these basic blocks is public. So we can generate highly optimized circuits that represent these basic blocks. So going back to our state transition function, so now we know that the program counter is public. So since we know that, we can fold away all these other circuitry that we needed before. And if, say, this was a XOR instruction, so now we're left with just the XOR in the circuit itself. So we can take this further by combining multiple instructions in the same basic block. So previously on the left-hand side, you would have to have 3 separate circuits to generate or to check each step of instruction. And then by using our public PC optimization, you can generate a highly optimized circuit that encodes all 3 of these operations. And then we also have some checks to ensure that you're able to jump between these private circuits and these public circuits using a routing network, and we have checks to ensure that that's done securely. So like I mentioned, we're able to encode memory vulnerabilities and detect them. So we're able to detect reads and writes before allocation, out-of-bound accesses, reads and writes after freeze, and then use after freeze. And like I mentioned, we've used this to prove vulnerabilities in GRIT and FFmpeg. So the high-level idea of our encoding is that anytime you see it have a memory allocation, you allocate the memory that the programmer requests, and then for memory out past the allocation, you poison those addresses. Anytime that there's an access, like a read or a write to poisoned addresses, you know that a vulnerability has occurred, and you can set the bug flag to true. And then we do the same thing for freeze, where we poison all of the memory in freeze. Okay, but so this works, but this is expensive, right? Because if you would need to poison every single address in memory. So what we do is we use a non-deterministic advice by the prover to know exactly where the vulnerability occurs in memory, and then use that. And we have special checks to ensure that the prover can't cheat and poison memory that they're not allowed to. We also have encodings for information leakage, and we use this to prove the OpenSSL Heartbleed vulnerability. So there's two different approaches that we considered to prove these sorts of vulnerabilities. The first is to use the naive non-interference definition, where you take two executions of a program, and basically if the low output of the program differs, even though only sensitive high inputs were different, then you know that a information leakage has occurred. This works, except it has a downside in that the circuit has to be twice as large because you have to generate two executions and simulate that in zero knowledge. So the approach that we ended up taking is that we used a taint tracking system where you mark data in your program as either secret or public. And then if the secret data is leaked to the attacker, to a channel that the attacker has control over, then you have proven that a leak has occurred in the program. So I'll talk a little bit about our zero-knowledge backend. And this is an interactive zero-knowledge proof system. So like our zero-knowledge proof system is called mac and cheese. So it's a backend for VOLE-based protocols. And it combines a bunch of different VOLE protocols in a highly optimized architecture. Currently, we have support for the Quicksilver protocol, and then we have our own support for disjunctions. And we're currently working on adding support for field switching, rings, and Ant-Man for optimized loops. So this kind of sets the scene of the whole Civ program. So when the program started, Wolverine was state-of-the-art, and it took 450 nanoseconds per AND gate. And where we are today is we've actually achieved 4.3 nanoseconds per AND gate. And we believe this is the fastest interactive zero-knowledge proof system that we know of. So how do we do this? Well, we have this highly optimized architecture. So we take as input any Bristol circuit, R1CS, CivIR, whatever circuit representation. We have a compiler. We compile it into our own mac and cheese IR. Our mac and cheese IR is broken down into a bunch of highly optimized tasks that need to be performed by the circuit. And then we have a runner that runs each of these individual tasks. So here's an example of compiling what an AES circuit looks like. So on the left, you have the AES circuit, and then on the right-hand side, you have the mac and cheese IR representation of this. You can see all the tasks are broken down, and each task is combined for just basically doing all the same operation. So this is highly optimized using SIMD optimizations, minimizing cache misses, and there's no branching, right? So it's very efficient. So the benefits of this architecture are that it's modular. We can easily add tasks. So we're planning on adding Ligero integration, support for RAM, polynomial checks, et cetera. And we can build more complex components from tasks. So you can add field switching by composing other tasks. It's also highly parallelizable. You can dispatch these tasks to different threads, and it's performant since each task is highly optimized to do the one thing it's good at. So here's a bit more on our performance and our experiments. So we ran this experiment across the United States, from the East Coast to the West Coast, from Virginia to Oregon. The circuit we benchmarked was 2.3 billion AND gates and 10 billion XOR gates. And you can see it only took 9.9 seconds with like the 4 point.
How many bits of communication per AND gate? That's the only thing that can be replicated here. So how many bits? I mean, just these numbers are very sensitive.
Yeah, I will have to get back to you, but I know we're not saturating the network bandwidth. So yeah, I can ask. And here's a comparison of software implementations versus our ZK implementations. You can see for AES we're actually about 100x slower for AES and 70 times slower than SHA. So for availability, we're planning on open sourcing our implementation soon. So reach out to us if you'd like early access. And if you have use cases that require or could use interactive ZK, we have a Dockerized testbed that we're happy to share and get some feedback from y'all from. So that's it for today. I just wanted to thank all the people who are on this project that have helped make this happen. People like Galois, our hosts, Columbia, and Get It. So thank you.
You mentioned this being interactive pretty much. Is this just because of the volley setup, or you need more interactions? Because these type of volley-based systems can be made non-interactive in principle given the volley setup. So I'm wondering whether interaction is inherent, assuming that you've already set up the correlated randomness for the volley.
So my understanding is that these protocols are interactive, but I think we can add support for non-interactivity with probably 1 or 2 orders of magnitude slowdown.
Orders of magnitude, okay, I see.
Probably 1 or 2, yeah.
Okay. Like even in the arithmetic, okay, I see.
Yeah.
Just follow up. So where would the order of magnitude of slowdown come? Is it just a Fiat-Shamir thing, or is it something else? The non-interactivity.
So I'm not a cryptographer. My background's in formal methods, but my understanding is
Okay.
yeah.
Never mind. Yeah, offline, yeah.
I wonder, I know that Galois also have formal provers unrelated to zero knowledge to prove cryptographic primitives, and they used it in many places already. And I wonder what is the similarities between these provers that can prove the correctness of memory and there are no bugs inside the code, and in relation to this architecture that also proves but tries to not prove it directly.
Right. So yeah, Galois has a bunch of formal method tools, so we can prove the correctness of like AES primitives or that sort of thing. I didn't present it here, but we also have the capabilities of proving unsatisfiability statements. So that's the groundwork for a lot of these formal method tools. So in theory, you could say hook up Cryptol or Sol, which are our tools, and then generate zero knowledge proof statements using the paper is called ZK Unsat. It's by Ning and all, if you want to look it up. But yeah, in theory, eventually we could do zero knowledge proofs of program correctness and security.
More questions? Okay, thanks again.
Thank you.